This is formal lab number 2, altering mass with the high air resistance in free fall. So for our research question, we chose to examine how altering the mass of an object that maintains a constant drag coefficient affects its terminal velocity. So as a bit of an introduction, the effect of adding mass to a highly air-resistant styrofoam bowl is observed upon tracking the bowl's motion during free fall. Due to the high air resistance of the bowl, it can be reasonably assumed that the bowl reaches terminal velocity relatively quickly. Tracker can be utilized to measure the motion of the paper bowl across different trials of different masses. So for our results, we'd obtained that predictably the trial with no additional mass added had the slowest terminal velocity. As more mass was added to the bowl, the terminal velocity increased.
All right, so here we have the free body diagrams for the bowl. The force of drag and the force of gravity are equal because it's following a terminal velocity. So the only difference between each one with or without mass is going to be the magnitude. With the mass, it's going to have a bigger magnitude, bigger forces because it's mass times acceleration, and then the smaller magnitude for the smaller mass. So that'll keep it consistent. All right, so in our system schema, we have the bowl and the earth as the only two objects. The only force acting on them is going to be gravity between the two, and then the schema is just going to be focusing on the bowl. All right, so here we have the energy pie charts. It starts with potential energy before it is dropped at 1.5 meters. It is then dropped and it starts to lose potential energy, and kinetic energy is gained. Internal energy is gained from air resistance. As it continues to drop, more kinetic energy is there, as well as less potential and more internal. And then at the end, it is going to have all internal energy based on the air resistance as it fell. So for our experimental design, we had a styrofoam bowl that we took the mass of, and then we proceeded to put 2 ball bearings in one and 4 ball bearings in the other. These were then weighed, and it was dropped from a height of 1.5 meters in those 3 tests. After that, we put the video into Tracker to track the data and give us the velocities.
So in regards to the scientific reasoning behind what's happening here, we started by looking at the drag force formula, which is the most applicable physics formula in this situation, and we defined all of our variables. So for example, the drag coefficient, the air density, the cross-section area are all remaining constant. V, the velocity, is the only one that is dynamic in this situation. Due to how we are presumably examining the motion of the falling bowl at terminal velocity, it can be assumed that the force of drag equals the force of gravity while this is occurring. Therefore, the vertical net force has to equal 0. Below are also the gravitational force calculations, which in effect will equal the drag force calculation. Going back to the drag force formula, because the gravitational force is equivalent to drag force at terminal velocity, we can assume that by altering gravitational force, we'll be directly altering velocity due to how they can be linked together mathematically in the formulas we've provided thus far. Due to drag force equaling gravitational force, as well as trying to link the given formulas together, it can be assumed that ma equals half c drag PAV squared. Everything but mass is being kept constant, thus a mathematical trend can be established between mass and velocity. When mass and velocity were plotted with mass as the independent variable, a square root relationship was established, and it is shown that because velocity has a quadratic relationship with a drag force in the formula, a square root relationship makes perfect sense because, in essence, you are doing the inverse. With our methodology of the experiment. First of all, tracking a styrofoam ball at terminal velocity turned out to involve much human error as well as software error with using Tracker. And in reality, 1.5 meters is arguably insufficient for a good observable fall distance in terms of mitigating user error. And the ball bearings were not perfectly aligned within the bowl to assume that you would be keeping the same drag coefficient throughout the experiment.